So it's a quick recap of what we saw in the Fourier. If you looked at the animation, this is a small animation of the sinusoids that we looked at. We create a certain period of time, and then for that period of time we create multiple sinusoids and we keep adding them. We start with nothing and we add the first one and second one and third one, and we see that this becomes a square wave. And so if we run this, the first harmonic in the top is the harmonic that is getting added, that's being shown. The amplitude is significantly coming down. The first one was a little more than 1, and by now the amplitude has gone down to 1/10. The net waveform, which is what is being drawn in the bottom, is becoming more and more like a square wave. So this is every next harmonic getting added. You can see that the frequency is getting higher and higher. There are more and more of the waveforms that you can see. And that's it. So this one is starting to look very much like a square wave. And if you just looked at the net wave and cleared out the previous net wave, let's just go a little faster this time. So let's just clear the figure and then just run this. So if you look at it, we can see that the waveform is definitely becoming more and more squarish. So it's not just that if we add sine waves in a certain way we can get a square wave. If you have any periodic wave, we should be able to represent it as a sum of sine waves with multiples of the fundamental frequency. So this will also be code that's available to you to play with. And if you look at the same for more complicated waveform, we saw that this was 8 divided by pi square n square, that's a square, and a slightly more complex expression. Then we can see that it's a sine wave and we keep adding higher and higher frequencies, that this starts to look more and more like a triangular wave. So this animation will also be available for you. And if you wanted just to look at the final waveform each time, we can clear the picture and then plot it, and we can do it a little faster this time. So you can see that the waveform is tending to be more and more like what you would expect the triangular wave to look like. Okay. So one thing to note in both the square waves is that we just had sine waves at the fundamental and many times 1, 2, 3, 4 of its harmonics, and even in the triangular wave it's the same. So what is different is mainly the what is the value of each of the sine waves, the amplitude of each of the sine waves. That's all that's changing from one periodic waveform to the other. So extracting this information is what is called Fourier series. So the Fourier series is the summation of sine waves or cosine waves at frequency of the signal as well as the harmonics of the signal, which is 2 times the signal, 3 times the signal frequency, and so on. And what we use is basically the orthogonality of sinusoid, which means that if I want to extract the information of a sine wave, as long as I multiply it with a waveform, all other information, so all other sinusoid and cosinusoids will actually go to 0, which is what we have seen before because of this relationship. So essentially, if I had a square wave, Or actually, if I had a strange looking waveform that looked like this, but it was periodic, which means it repeated, but it looked like that. Then all I need to do is I need to multiply it with sine wave of the fundamental frequency and average it. That's it. And the component, the energy that it had at the fundamental, at this frequency, would multiply with the energy at this frequency. The sine will multiply with the sine, becoming sine square, and sine square average will be, so a, whatever is the amplitude a, if I multiply it with the unit sine wave, then a into sine square will become a by 2. So the different components at each of the frequencies is simply the, you just have to multiply it with the waveform you want and average it. That's it. Okay, so let's give this a field test. So here's my time, and if I look at the length of time, I have almost 100,000 points, one shot of 100,000 points. So if I just create another array, and then the length of b would be the same as the length of a, and if I plot b, it will look the same as a. So if I find the plot, there it is. So now I want to generate that strange looking waveform. So I just make I make everything equal to 0. Colon just means make everything equal to 0. I have to plot it after that. Oh, 1 second. It's plotting two things. Yeah. So now it's 0. Now I go back to Python. Now I say from the beginning up to half the length, make it 1. Clear that old plot, plot the new thing. So now if I look at the plot, well, with 0 and 1 it may be a little hard to say, so we pan it a bit. Yeah, there you go. It's 1 till there, half the values, and after that it's 0. Okay, the next part of the waveform is a little tricky, so I'll go through it slowly. In the rest of the half, I want from half to 3/4 of the waveform, the waveform to go down and look like a triangular wave, which means I wanted to go from 0 to 1, and I wanted to go very slowly, so the step size is 1 by 1/4 of the total number of points, which is what is length of b divided by 4, 1 over that, so that's why it's 4 divided by length of b. I didn't clear the plot, I should have. Okay. So there we had our square wave, and now it's gone down, then of course it's 0. Now I just need to get the flipped version of this, so from -1 to 0 I need to just go up. And the way I've done that is I've said 1 to 0 I have to go down, and it's minus of that. I could also have said exactly what I said. -1 to 0 I go up. Clear the old plot, get the new plot. So that gives us what we wanted, which is a square wave, and then after that a triangular wave. Okay, so the most simplistic way of doing this is to just generate sine waves of first harmonic, second harmonic, third harmonic, and cos waves, because it's a combination of sine and cos. Cos waves are first harmonic, second harmonic, and third harmonic, and then so let's do that for the first one. So let's multiply with this, let's clear that, let's have the signal also with us. So I have the sine wave, and now I multiply it with the sine wave. Let me plot it. So we see that we have our square wave, and we want to multiply it with the sine wave, it stays the same, and the negative cycle, this is also going negative and that is also going negative, so that it will have some average value. Let's do the same with the cos wave. So I have cos wave form, the other cos wave form. Let's clear all the other things, plot it again, and there, multiply it, basically plot d1. What does that look like? Yeah, so now we see that it was positive here, it becomes negative there, so when you average this, this basically blows away, which is why for a square wave it becomes 0, because it would be the same repeated 2 times and it will sort of cancel out. Now in the case of a square wave and a triangular wave, you also have a triangular wave. Oh, yeah, even this goes off. So if I took the average value of d1, it should be very close to 0. It's 10 power minus 6. So this waveform doesn't have a cos component. So you can see that. Okay, let's see second harmonic. Sine 2, sine 2. So now if I clear everything, plot just this waveform, original waveform, and I plot the second harmonic multiplied by the waveform. So I see that the second harmonic goes up, comes down. This part, if I average out, will be 0, 2. So this doesn't give me any contribution. And how about this one? Well, this also looks like it's sort of symmetrical across this. It blends it and then it comes down. And okay, so it looks like if I took a mean of that, then A2S is also 0. So this doesn't have a second harmonic sine component. It doesn't have the first harmonic cos component. Let's see third harmonic of sine. So we can see that if the waveform is symmetric across half or 1/4 of the period, if you think about it, this side and that side, this side and that side, then the second harmonic will always have a period going up, coming down, cancel out, going up, coming down, cancel out, and the fourth harmonic will have one period and another period, one period and another period, and will also cancel out. So let's look at the third harmonic, which is this one. So as before, we clean everything, we only plot the original waveform, and then now we plot this. Oh, we haven't plotted it yet, sorry. Okay, let's see. So it has a positive half and then it has a negative half, so these two cancel out. And then it has a positive half, so there is some component because of that. Similarly, it has a positive half, but the negative half is a little larger, so maybe this is a bit of a wash. So it certainly has one lobe, so there will be some value because of it.